everybody, in this video we are going to be going over radicals and exponents. So we're going to start off with just a quick refresher of how do we find square roots or cube roots, what does the radical symbol mean, and so we're just going to explore that a little through some problems that you're probably somewhat familiar with. All right, so the first question says find the square root of 16. Okay, so just a couple of brief reminders. This symbol here is called the radical. All right, the stuff that's under the radical is called the radicand. So the stuff that's under the radical, the expression that's under the radical, is called the radicand. And in this little check mark right here is the index, right? So you can see that there's no index indicated here. If there's no index indicated, and what I mean by that is if there's no little number in the check mark, right, so if there's no index indicated, that means that it is a square root and the index is 2. Right, so if it's a square root, you do not have to write the index of 2, but you can if you want to. What the index tells you is I'm looking for something that I can multiply by itself twice and get 16, so get the radicand. So what number can I multiply by itself twice and get the radicand? Right, so what number can you think of that we could multiply by itself to get 16? That would be 4 times 4, right? 4 times 4 is 16. All right, so let me show you what this process looks like. All right, so you start off with your square root of 16 and you say, okay, well 16 is the same thing as 4 squared. So 4 squared means 4 times 4. All right, so 4 squared means 4 times 4. Right, and we also know that there is this understood 2 there in the index. All right, and when your index matches your exponent, they cancel each other out. Right, when the index matches the exponent, they cancel each other out, and that leaves you with 4. All right, so 16 is what we call a perfect square. So 16 is a perfect square, which means that we can find a whole number that you can multiply by itself to get 16. I think it's smart to have at least the first 10 perfect squares memorized. So the first 10 perfect squares, that'd be like 1 squared is 1, 2 squared is 4, 3 squared is 9, and then all the way to 10. 10 squared is 100. All right, so I would suggest that you have the first 10 perfect squares memorized, maybe even to 15. So maybe even all the way to 15. So 11 squared, 12 squared, all the way to 15 squared. If you don't want to have those memorized, you can just put them on your formula sheet. 11 squared is 121, 12 squared is 144, 15 squared I think is 215, but let me check. 15 squared, 225. All right, 15 squared is 225. All right, so again, if you don't want to have those all memorized, just put them on your formula sheet for our next quiz or exam, because it is useful to be able to recognize those perfect squares. All right, let's do another example. All right, so next we have the square root of 64. All right, so again, it's a square root. We know that because there's no index indicated. So we're assuming that that's a 2 there in the index and that that's a square root. Now we're asking ourselves, what can I multiply by itself to get 64? That would be 8, right? 8 times 8 is 64. So 64 is the same thing as 8 squared. We know that there's a little index of 2 there. And when your index matches your exponent, they cancel each other out, which leaves you with 8. So 64 is also a perfect square. 64 is a perfect square. Most numbers are not perfect squares, so like if you had something like square root of 63, 63 is not a perfect square, but we can simplify that. And we'll talk about that actually on the next page. And then we'll do a little extra example and do square root of 63, so you can just see some additional examples. All right, so let's look at an example of something that's not a perfect square. All right, so this one says find the square root of 27. All right, so if you are trying to simplify a square root that is not a perfect square, your first step is going to be to determine the largest perfect square that is a factor of the radicand. So basically, you're trying to ask yourself, what two numbers multiply to 27, one of which is a perfect square. All right, so let's try to think of some numbers that multiply to give you 27. Definitely 1 and 27, right? 1 is a perfect square, but that's not really going to help us. All right, so another factor pair of 27 would be 3 and 9, right? And 9 is a perfect square. 9 is 3 times 3. All right, so we found a factor pair where one of our factors is a perfect square. All right, and so after you've done that, your second step is to use what we call the product rule to factor out and simplify that perfect square root. All right, so let's look at an example here. All right, so let's say we have square root of 27. Now, what I like to do is I like to take my factor pair and I'm going to say, okay, well, 27 is the same thing as 3 times 9, but I'm going to be very intentional the way I write this, and I always write the perfect square factor first. All right, so I always write the perfect square factor first, and that's intentional. All right, so I'll do square root of 27 is equal to the square root of 9 times 3. Notice that perfect square factor went first. And then I separate this, and this is what we call the product rule. And it just says if you have the square root of a number times another number, you can just separate that into two separate radicals. So you can separate that into square root of 9 times square root of 3. So you're just really taking your radicand and you're separating this into two separate pieces. And now that I have used the product rule to factor out my perfect square factor, I'm now going to simplify, right? And I know that the square root of 9 is 3, right? So this reduces or simplifies and becomes 3. And you're left with 3 times the square root of 3. You can drop the little dot in the middle. You don't have to have the little dot in the middle. And there's lots of different ways that you can read this. The way that I typically read this is 3 root 3. But you could say 3 times the square root of 3. I have heard some people say 3 on the square root of 3. Okay, so lots of different ways that you can read that out loud. And let's see, there was one more thing I wanted to say. Square root of 3, there's no factors of 3 that are going to make this any more simple. The only things that multiply to 3 are 3 and 1. So this square root is not going to be able to be broken down any further, but that is something that you should check before you circle and, you know, decide that that's your final answer. You should look at your radicand and say, okay, is that in its simplest form? Is there anything else that I could do to split this up into two perfect square, or excuse me, into two factors, one of which is a perfect square. All right, let's look at that square root of 63 example, and then we'll move on to cube roots. All right, let's say we have square root of 63. All right, so 63 is not a perfect square. There's no number that you can multiply by itself to get 63, but there are lots of things that multiply to 63. Let's see, of course, 1 and 63. I'm pretty sure 2 goes into that. 63 divided by 2, nope, it doesn't. 63 divided by 3 is 21. Okay, so 3 times 21, that doesn't really help us. 3 is not a perfect square, 21 is not a perfect square. Let's see, 4 does not go into it, 6 does not go into it, but 7 does, right? 63 is 7 times 9. 9's a perfect square, right? So that's helpful. All right, so let's take and rewrite square root of 63 as the square root of, remember, and I'm always going to put the perfect square first, so 9 times 7. Right, then I'm going to use the product rule, which says that if you are multiplying inside the radical, you can split that up into two separate pieces. All right, so square root of 9 times square root of 7. And then I'm going to go ahead and simplify that perfect square. The square root of 9 is 3. All right, so the square root of 9 is 3. Now I can drop the little dot in the middle and just write square root of 7. Right, so 3 times the square root of 7, or 3 root 7, or 3 on the square root of 7. So again, lots of different ways you could read that out loud. All right, so let's look at a cube root example. All right, so here is a cube root example. You can see that the index is clearly indicated right here. All right, so we've got the cube root of 8. And when you're dealing with cube roots, you're asking yourself, what can I multiply by itself 3 times? So the index tells you how many times am I multiplying this number by itself. What can I multiply by itself 3 times to get 8? All right, so what can you multiply by itself 3 times to get 8? What about 2 times 2 times 2? 2 times 2 is 4. 4 times 2 is 8. All right, so let's look at how this is going to be written out. All right, so the cube root of 8 is equal to the cube root of 2 cubed, right? Because 2 times 2 times 2 is 8. All right, so again, just to remind you, this whole section is about exponents and radicals, so I'm trying to not assume that you know all this stuff. 2 times 2 times 2 can be written as 2 cubed, 2 to the 3rd power. And remember the rule we said earlier when we were dealing with square roots is if the index matches the exponent, these are going to cancel each other out. So here the index matches the exponent, they cancel each other out, and that's equal to 2. All right, so 8 is what we call a perfect cube. 8 is what we call a perfect cube. All right, so just like we said with perfect squares, a perfect cube is just a number that, you know, is when you take the cube root of it, it's equal to a whole number. All right, so our first few perfect cubes, of course, 1 cubed is 1. 2 cubed, we just said, is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed, I think it's 216, but let me check. Yes, 216. Let me see what 7 cubed is. 343. I never used that one. I don't know why. Right, so I would say 6 is really as far as you need to memorize. I don't typically do anything higher than 216 with the cube root problems. All right, so make sure you write these down, put them on your formula sheet, or have them memorized before we go into our next quiz or test. All right, and let's look at one more example. All right, so this one says find the cube root of 125. We just saw that number, so that should look familiar. The cube root of 125, right? We know that 125 is the same thing as 5 times 5 times 5. Right, so 5 times 5 times 5 is 125. Right, so we can rewrite 125 as 5 cubed. And remember, when our index matches our exponent, they're going to cancel each other out. So cancel, cancel. That's left with 5. Right, so 125 is also a perfect cube. Right, so let's look at an example where we have a number that is not a perfect cube. All right, so we have the cube root of 54. All right, so very similar process to what you saw before with simplifying square roots. All right, so if you have a number that is not a perfect cube, you're going to find two factors, or let's just say find two numbers. Find two numbers that multiply to, in this case, 54, comma, one of which is a perfect cube this time. Right, so when we were doing the square roots, we wanted one of the factors to be a perfect square. Since we're doing cube roots, we want one of the factors to be a perfect cube. Okay, so let's think of things that multiply to give you 54. Of course, 1 and 54. Let's see, is it divisible by 2? Yes, it is. 27 times 2. And then, let's see, 3. Is it divisible by 3? Yes, 18 times 3. And then I'm thinking of 6 and 9, right? 6 and 9. Multiply to give you 54. All right, are any of these numbers perfect cubes? Look at our numbers. 2, 27, 18, 3, 6, 9. Are any of those perfect cubes? 9 is a perfect square. That's not really helpful. We're looking for a perfect cube. 6 is not a perfect cube. 3 is not a perfect cube. 18, no, that's only 2 times 9 or 6 times 3. But 27 is a perfect cube. Remember, that was in that list from the last slide. 27 is 3 times 3 times 3. Right, so 27 is a perfect cube. Right, so that's the ones we're going to use. Right, so we're going to split up 54. We're going to say, okay, 54 is the same thing as 27 times 3. And notice I'm doing the same thing here. I'm writing the perfect cube first. Right, and that's intentional. I like to have the perfect cube in the front, so whenever I separate this into two pieces, the perfect cube or the perfect square is at the front. All right, so now I'm going to split this up into two separate radicals. I'm going to do the cube root of 27 times the cube root of 3. I know that 27 is a perfect cube. It is 3 times 3 times 3, so that means that 27 is the same thing as 3 cubed. This number here cannot be simplified, so we're just really dropping it down. Now over here on the left, the index matches the exponent, so those are going to cancel each other out. That leaves you with just 3. The radical's gone now, it canceled out. So we have 3 times the cube root of 3. Right, so 3 times the cube root of 3. And that's our final answer. Again, 3 is not a perfect cube. There's nothing that we could break 3 down into. There's no factors that multiply to give you 3, one of which is a perfect cube, so we will just leave it alone. Right, so let's look at some properties of radicals. Right, so that first one, you've already seen that. That's called the product rule. That's called the product rule. Right, and it just says that if you have the square root of a number times another number, so a times b, then you can split that up into two different radicals, so square root of a times square root of b. An example of what this might look like, we've seen this a couple times now, but maybe something like 100 times 2, square root of 100 times 2. You can separate that into square root of 100 times square root of 2, and then you could simplify that and say, okay, well, I know that 100 is a perfect square. The square root of 100 is 10. And the square root of 2, that cannot be simplified, so you just leave it square root of 2. This second rule is called the quotient rule. The quotient rule is very similar to the product rule, and it just says that if you have a quotient or a fraction inside of your radical, you can split that up into, the square root of the top over the square root of the bottom. So if you had something like square root of 4 over, let's do 81. Right, you could say, okay, well, that's the same thing as square root of 4 over the square root of 81, and then simplify each of those. 4 and 81 are both perfect squares. The square root of 4 is 2, and the square root of 81 is 9. 9 times 9 is 81. All right, so product rule and quotient rule, very useful. Now, two properties that you will not see, this does not work, but it's a common mistake, so I want to point it out to you. So what I'm about to show you, this does not hold. This is not a property of radicals. You can't take something like 100 plus 50 and separate that into square root of 100 plus square root of 50. Right, so that does not work. And same with addition. With subtraction. So this is not equal. And then similarly, if you have something like, let's say, square root of 25 minus 5, you cannot separate that into square root of 25 minus square root of 5. Right, so that is not allowed. These are not true. Right, so the only time you can separate the radicals and break them up into two separate radicals is when you are dealing with a product or dealing with a quotient. So not with addition or subtraction. Right, so there is no sum rule or difference rule. So there's only a product rule and a quotient rule. All right, so let's look at a couple of examples. All right, so number 7 says multiply and simplify. You're also going to see this on the homework, so I would say it's very likely that you're going to see an example like this on the on our next quiz or exam. All right, so it says part A is square root of 5 times the square root of 20. All right, so this is kind of what we saw as the right-hand side of the rule. This is what our rule looked like. A times B, square root of A times B is equal to the square root of A times the square root of B. All right, so right now we're dealing with something that looks like the right-hand side. All right, so we're going to go over to the left-hand side and we're going to just combine this into one radical. All right, so we're going to combine this and say, okay, this is the same thing as the square root of 5 times 20. What is 5 times 20? It's 100, right? So that's the same thing as the square root of 100. Well, 100 is a perfect square. It's 10 squared. Right, and remember, this is a square root, so the index is 2. It's not written, but it's understood that that's an index of 2. And when your index matches your exponent, they cancel each other out, so the radical cancels with the exponent, and you're left with just 10. Right, now let's look at an example with a cube root. All right, again, we're dealing with something that looks like the right-hand side of this product rule. All right, so we're going to take it and combine it into one radical. All right, so we are going to combine this and say, okay, well, this is the same thing as the cube root of negative 3 times 9. What is negative 3 times 9? negative 27, right? So that's the same thing as the cube root of negative 27. Now you want to ask yourself, we know that 27 is a perfect cube. How could we get negative 27? Right, we know that 27 is 3 times 3 times 3, or 3 cubed. What about negative 27? What if we did negative 3 times negative 3 times negative 3? Negative 3 times negative 3, that would give you a positive 9. But when you multiply it times negative 3 again, that gives you negative 27. Right, so this is negative 3 cubed. Right, negative 27 is equal to negative 3 cubed. All right, so we've just rewritten negative 27 as negative 3 cubed. We know that when the exponent matches the index, these cancel each other out. So the cube root cancels with the cube, and that leaves you with just negative 3. Okay. All right, we got a few more. This time we're going to do divide and simplify. All right, so again, the directions are divide and simplify. Sorry for this little line that's showing up. You'll see why that's there in just a minute. So our first example says the cube root of 5 over 8. All right, so we are going to split that up and do the cube root of the top divided by the cube root of the bottom. All right, so cube root of the top over cube root of the bottom. Now 5 is not a perfect cube, and it doesn't have any perfect cube factors. The only thing that multiplies to 5 is 5 and 1, it's prime. All right, so we're just going to leave this alone. So just leave the numerator alone. But we do know that 8 is a perfect cube, right? 8 is a perfect cube. 8 is a perfect cube. Remember, 8 is 2 times 2 times 2, or 2 cubed. All right, so the top stays the same. The bottom has changed to 8 is the same thing as 2 cubed. And down here in the denominator, when our index matches our exponent, that cancels each other out. So a cube root cancels out a cube. All right, so in the bottom, we're left with 2. In the top stayed the same, cube root of 5 over 2. All right, there's nothing else we can simplify, so we're done with that one. Now let's look at the cube root of 16 over 300. You can see that I said cube root, didn't I? I meant to say square root, sorry. The square root of 16 over 300, I've just separated that into square root of the top divided by square root of the bottom. 16 is a perfect square, right? What is the square root of 16? The square root of 16 would be 4, right? So 16 is the same thing as 4 squared. We know that there's a little understood index of 2. Right, but what about the bottom? Let's think of 300 is not a perfect square, but it does have perfect square factors. Right, 300 can be written as 100 times 3. 100 is a perfect square. So let's split that up and say, okay, well, 300 is the same thing as 100 times 3. Up here in the top, a square root cancels with a square, so those two cancel. All right, so we're going to be left with 4 in the numerator. We're going to go ahead and split this up into square root of 100 times square root of 3. All right, so now you see why that line was there. Square root of 100, 100 is a perfect square. We know that this is the same thing as 10 squared. And again, a square root cancels with a square. Right, so that leaves you with 4 over 10 times the square root of 3. And normally you would be done at this point, but since 4 and 10 both are divisible by 2, we do have to simplify this. So just ignore the radical for a minute and just think of it as if it was 4 over 10, right? You would say, okay, well, this is not in simplest form. 4 is divisible by 2, 10 is divisible by 2, so you would divide the top by 2, divide the bottom by 2, that becomes 2 over 5. All right, so same thing's going to happen here. 4 over 10 reduces to 2 over 5, so that becomes 2 over 5 times the square root of 3. Now, typically in a traditional algebra class, you would not be allowed to leave radicals in the denominator, but I'm fine with it in this case. What I want you to focus on is being able to simplify the radicals rather than worrying about getting rid of radicals in the denominator. All right, so it's okay to leave radicals in the denominator for this class. What I want you to focus on is just being able to simplify the radicals. All right, so we talked earlier, we said that unfortunately there is no addition rule and subtraction rule for radicals where you can take something like, the square root of 25 plus 5 and split that up into square root of 25 plus square root of 5. All right, so unfortunately there's no rule that allows you to do that. So I do need to show you what we can do when we are working with addition and subtraction of radicals. And the way that we deal with this is we treat radicals like they were like terms. So for example, if you had something like 3 times the square root of 2 plus 5 times the square root of 2, you're just going to treat this as if it was something like 3x plus 5x. Right, so those are like terms, and you would say, okay, well, these are like terms, so I'm going to add their coefficients. So 3x plus 5x becomes 8x. All right, it's the same thing here. It's just that x is being replaced by the square root of 2. So think of square root of 2 as like your variable. Right, so you are just adding their coefficients. In this example, if it was subtraction, you would be subtracting their coefficients. Right, so you're just going to treat these as if they are variables or as if they are like terms. All right, so let's look at our first example. All right, so it says add / subtract and simplify. Starting with an easy one, we have 10 times the square root of 11 plus 4 times the square root of 11. You can think of square root of 11 as like our like term or our variable, and we're just going to combine the coefficients. So 10 plus 4 is 14. And then our like term is square root of 11. So 14 times the square root of 11. All right, and then this one a little bit harder because we have some simplifying we need to do first. They're not like terms at the moment. We've got square root of 12 plus 7 times the square root of 3. All right, so we would like both of these to for the square roots to match, for the radicals to match. All right, so let's try to work on this larger radicand. That's where you always want to start. You want to start with the larger radicand and make it match the smaller radicand. Right, I know that 12 can be rewritten as 4 times 3. I'm choosing that factor pair because 4 is a perfect square. Right, 12 is also 6 times 2. That doesn't help me because 6 and 2 are not perfect squares. Right, but 4 is a perfect square. All right, so we're going to separate that and say, okay, well, this can be broken down. Again, we're just kind of ignoring this right now. And we're saying, okay, this can be split up and written as square root of 4 times square root of 3. We know that 4 is a perfect square. Square root of 4 is 2. All right, so that's going to become 2 times the square root of 3. All right, so 2 times the square root of 3 plus 7 times the square root of 3. All right, so now we've got these matching. So now they are like terms. So we're just going to combine the coefficients. So 2 plus 7 is 3, or sorry, 2 plus 7 is 9. So that's going to be 9 on the square root of 3. Okay. Right, next we have a similar example, this time with a cube root. This time it's subtraction. Right, so remember what we're going to do here. Our goal is to make the radicals match if possible. So we're going to try to work on this larger radicand and hopefully make it match the smaller radicand. Right, so we have 5 times the cube root of 27 minus the cube root of 3. Right, but if you remember from earlier, 27 is a perfect cube. Remember, so if you have it written down, you can look at your list of perfect cubes. 27 is a perfect cube. It's 3 times 3 times 3, so 3 cubed. The cube root of 3, that can't be simplified. 3 is prime. There's no factor pairs we could break that down into, so we're just going to drop that down. Right, so now we need to simplify over here. Notice that our index matches our exponent, so these are going to cancel each other out. So the cube root cancels with the cube. The operation here is multiplication. There's no little dot, but we know this is multiplication, so we're now going to multiply these. 5 times 3, and then this side is just dropping down, so minus the cube root of 3. 5 times 3 is 15, minus the cube root of 3. There's no like terms here. We don't have a cube root of 3 that's attached to 15, so there's nothing else that we can combine. All right, so sometimes you might not be able to combine them, and that's okay. The only time you can combine them is when the radicals match. Right, so here the radicals almost matched, right? It was the cube root of 3, but it was 3 cubed, whereas this one's just the cube root of 3. Right, so they almost match, but not quite. Alright, so now we're moving on to the last half of this week's lesson, which is exponents. So we're going to start by looking at some properties of exponents. A lot of these should be familiar to you, but I am going to show you an example of each property. Alright, so the first property that we're going to look at is called the product rule for exponents. Now what this says is that if you have a common base, so if your base is the same, so here it's x to the a times x to the b, so if your base is the same, then you can combine those exponents. And here, if you are multiplying these terms, you add the exponents. So if you have a common base, again, this only works if you have a common base. Then if you're multiplying those, you can add the exponents. So let's look at an example of that property. If you had something like 2 to the 5th times 2 to the 3rd, notice that the base matches. They're both 2's. Since we're multiplying these, we would add the exponents. Right, so 2 to the 5th times 2 to the 3rd would become 2 to the 8th. Right, next we have what we're calling our negative exponents rule. In any algebra class that you take, you're always going to see the directions say write your answer with positive exponents only. Right, so we have to have a way to deal with those negative exponents, and this is how we deal with them. If you have something like x to the negative a power, then you can just imagine that this is like a fraction. Right now it has 1 in the bottom, and you take whatever has the negative exponent. Oops, sorry. Whoa. I don't know what happened there. Sorry about that. So you take whatever part of your expression in the top has the negative exponent, and you just flip it to the other side, or you send it to the other side of the fraction bar. All right, so that becomes 1 over x to the a. And then similarly, if you had a negative exponent in the denominator, you would take that piece and you would flip it to the other side of the fraction bar, and it would go to the numerator. And then that would be that would turn into a positive exponent. 1 times x to the positive a is just x to the positive a. All right, so let me show you an example of this. 3 to the negative 5th power is the same thing as 1 over 3 to the 5th. Right, and then similarly, 2 over x to the negative 4th. Right, we can move that piece that has the negative exponent to the other side of the fraction bar, and that becomes 2 times x to the 4th. Now I do want to show you one extra example. I just thought of this. If you have something, let's say something with multiple pieces, and it looks like this: 2 times x to the negative 3. Okay, and if you want to write this without negative exponents, so you want all your exponents to be positive, you would say, okay, I'm going to pretend like this is over 1, and you're just going to move the piece that's got the negative exponent. You leave that 2 alone. Leave the 2 alone. It doesn't have a negative exponent. It's fine. The piece that's not fine is the piece with the negative exponent. So you're going to take that and move it to the other side of the fraction bar. The 2 stays in the top. In the bottom we have 1 times x to now the positive 3, which is just x to the positive 3. Okay, so you're only moving the piece or the part of the expression, the term, whatever you want to call it. You're only moving the term that has the negative exponent. The ones that don't have a negative exponent, you just leave them alone. Leave them where they are. All right, next we have pretty useful little property, negative exponent rule for fractions. So if you have a fraction being raised to a negative exponent, you can easily take care of that by just flipping the fraction. So x over y to the negative a is the same thing as y over x to the positive a. Right, so for example, if you had 5 over 4 to the negative 2 power, you would just flip the fraction inside and that would change to a positive 2. So that's 4 over 5 raised to the positive 2. That's a very useful little property there. Can quickly get rid of negative exponents. All right, and then our quotient rule for exponents says that if you are dividing 2 terms that have a common base, right, so just like when we're looking at property number 1, these 2 have a common base. Right, so x to the 8th power divided by x to the bth power, you can combine those into one term and you subtract the exponents, and it's always numerator's exponent minus denominator's exponent. So in this case, it's always exponent of numerator minus the exponent of the denominator. All right, so it's always numerator minus denominator. Okay, and again, that only works if you have a common base. So let's look at an example. If you had, say, 5 to the 10th power over 5 to the 8th power, these have a common base of 5, so we can combine these. And since we are dividing, we're going to subtract the exponents. Let me get this out of the way since it looks like that's going to be in the way. Okay, so if you have a common base, you can subtract the exponents when you're dividing. So that would be 10 minus 8, 5 to the 10 minus 8, which is 2. All right, we have a couple more properties. First one is called power rule for exponents. I always call this one a power to a power. So this one, I always call this a power to a power. Right, if you have a power being raised to another power, you multiply the powers. Right, so a power being raised to a power, you multiply them. An example of that, let's say if we had 7 squared raised to the 4th power, you would say, okay, this is a power to a power. I'm going to multiply them. 2 times 4 is 8. So that'd be 7 to the 8th power. All right, and this one, I think of this rule or property number 6 as more of like a distributive property than a power rule, but that's what the book I was referencing called it, so that's what I'm calling it as well. And it just says that if you have some expression inside of a parentheses, it's a product, and you're raising all that to a power, you got to make sure and distribute that power to both terms. So that becomes x to the a times y to the a. All right, and an example of this, something like 2x raised to the 5th, so 2x inside the parentheses raised to the 5th power. You would make sure and say, okay, I've got to distribute this power to both terms. So that's going to become 2 to the 5th times x to the 5th. And then you could go on and simplify and say, okay, 2 to the 5th is, I want to say that's 32, but don't hold me to that. Let's see. 2 to the 5th. Yes, it is 32. All right, and then our last property, very similar to property number 6, and it just says that if you have a fraction that's being raised to a power, you got to make sure and distribute that power to the numerator and to the denominator. All right, so an example here, 2 over 3 to the 4th. All right, you got to make sure and say, okay, well, I'm going to distribute this exponent. It's got to go to the numerator and the denominator. So I'm going to do 2 to the 4th over 3 to the 4th. Okay, let's look at some examples. All right, so simplify the expression. Your answer should contain only positive exponents. All right, so we have 2m squared times 2m cubed. All right, you're going to start by just multiplying the coefficients. 2 times 2 is 4. All right, now you're going to deal with the variables. So m squared times m cubed. M squared times m cubed. These have a common base of m, and they're being multiplied. So we're going to add the exponents. So that's going to become m to the 5th. All right, next one, very similar. It says x to the 4th times 4x to the negative 3. There's no coefficient on this first one, but you can pretend like there's a little 1 out there. All right, then you can say, okay, I'm going to multiply my coefficients. All right, so 4 times 1 is 4. All right, then I'm dealing with my variables. We have x to the 4th and x to the negative 3. Don't worry about that negative 3 yet. We'll take care of the negative stuff. That's always like the very last thing that I like to take care of, because sometimes it kind of works itself out. So don't stress about the negative exponents yet. So this is really what we're dealing with right now. X to the 4th times x to the negative 3. We've got a common base of x. These have the same base. They're being multiplied, so I'm going to add their exponents. All right, what is 4 plus negative 3? That's really the same thing as 4 minus 3, right? So that's 1. So that's going to be x to the first power. Now we don't need to write the first power. You can leave that off. So I would write the final answer as 4 times x. Okay. All right, so our next one, same directions. This one says 3 times y to the negative 3rd power divided by y squared. Now there's a couple of different ways you could deal with this, but I'm going to be utilizing the quotient rule for exponents, which is what we use when we have a common base. These two terms have a common base of y. Now we do have this 3 out front. It doesn't have a negative exponent, and there's nothing we need to do with it, so it's just really going to come along for the ride. So it's going to stay up there in the numerator. But let's talk about how we're going to deal with these variable pieces or variable terms. All right, so we have y to the negative 3 over y squared. The quotient rule for exponents says if you have a common base, you can subtract. If you have a common base and you are dividing, you can subtract the exponents. All right, so that's going to become 3. And notice that the fraction goes away after you do this. All right, so the fraction is going to go away. It's going to be 3y to the negative 3 minus 2. Right, so I am subtracting the exponents. I'm doing the numerator minus the denominator. So negative 3 minus 2. Right, now I'm going to combine those. That's going to be 3y to the negative 5th. And remember, I'm not allowed to leave negative exponents in my answer, so I am going to have to deal with that now. And remember, the way I deal with that is I pretend like this is over 1. And then I'm going to take the term that has the negative exponent, and I'm just moving it down to the other side of the fraction bar. All right, so the 3 is going to stay up there in the top. It does not have a negative exponent. There's nothing wrong with it. So we're just moving down the piece or the term with the negative exponent, and that's going to become positive. So it's 3 over y cubed. 3 over y cubed. Whoa, whoa, whoa. 3 over y to the 5th, sorry. 3 over y to the 5th. Right, next we have 2y squared times 3x. All right, so we're going to deal with the coefficients first. All right, so go ahead and deal with those coefficients. 2 times 3 is 6. Now let's take a look at what's left over. We have a y squared, we have an x. Those do not have a common base. All right, so y squared and x do not have the same base. So that means we can't combine them. That's okay. I like to write my variables in alphabetical order, so I'm going to put the x first and the y squared second. That's not necessary. You don't have to do that. But I like to do that just to make it look, a little bit neater. All right, so I like to put my variables in alphabetical order. All right, next we've got a little bit more complex looking expression here. We're going to start by looking at what we have here. 4a cubed b squared times 3a to the negative 4th b to the negative 3rd. All right, so go ahead and multiply your coefficients. 4 times 3 is 12. All right, so 4 times 3 is 12. Right, now we're looking at our a's. We have a to the 3rd, a to the 4th. Right, we're multiplying, so we're going to add those exponents. So that's 3 plus negative 4. Right, now let's look at our b's. B squared, b to the negative 3rd. Right, so again, we're going to add those exponents since those have a common base of b. So 2 plus negative 3. All right, so let's combine like terms, or excuse me, not combine like terms, let's simplify. Sorry. 12 is just going to drop down. 3 plus negative 4, that's negative 1. 2 plus negative 3, that's also negative 1. So that's going to be 12 times a to the negative 1, b to the negative 1. All right, then we've got to take care of those negative exponents. Remember, those are not allowed to stay. Our answer should contain only positive exponents, so we're going to pretend like this is all over 1. Then we're just going to take the terms with the negative exponents, which is the a to the negative 1 and the b to the negative 1, and those are going to get moved down to the other side of the fraction bar. The 12 is going to stay where it is. It does not have a negative exponent. It does not need to get moved. Right, so that becomes 12 over a to the 1, b to the 1. So the exponents have now become positive. And we don't have to write the ones, right? We can leave those off. So that would be 12 over a times b. Okay. All right, we're almost there. We've only got a few more. Same directions. This one says x squared raised to the 3rd. So we've got a power to a power. So we're going to multiply those. 2 times 3 is 6. So that's going to be x to the 6th power. All right, next we've got 4a cubed raised to the 2nd power. Now this is the one that I told you that I like to think of this as like a distributive type of property. So that power of 2 is going to get distributed to the 4 and to the a cubed. So we've got 4 squared times a cubed squared. Right, 4 squared is 16. Right, then we've got this power to a power here. We've got to deal with that. So a power to a power, you multiply them. So 3 times 2 is 6. So we've got a to the 6th. So 16a to the 6th. Right, next we've got one with a negative exponent. Right, so the way that I was thinking of this is I thought, well, I would try to think of this as like a negative exponents rule. And I would say, okay, well, I'm just going to pretend like this, everything is over 1 here. Right, so I'm going to pretend like this is a big fraction where everything is over 1. All right, so I'm going to flip that. And whenever I flip that fraction on the inside, it's going to make that exponent positive. Right, so I'm going to flip that. It's going to become 1 over 4xy. And that negative 1 changes to a positive 1. Right, now when I raise something to the first power, it just stays the same, right? So 2 to the first power is just 2. 3 to the first power is 3. 100 to the first power is 100. Right, so raising something to the first power does not change it. So I can really just drop the first power, drop the parentheses, and there's my answer. This is our most challenging problem so far. We've got a lot going on here, so let's just read the problem. It says 2x to the fourth, y to the negative fourth, z to the negative third, and then 3x squared, y to the negative third, z to the fourth. Right, so we always start by dealing with our coefficients. So 2 over 3, that doesn't reduce. There's nothing that I can simplify there. So I'm just going to leave those alone. They're just going to, tag along as we simplify this. Right, then I'm going to use the quotient rule for exponents because I've got these little pairs of variable terms that have common bases. Right, so I've got the x's, that covered, use a lighter color. Right, then we've got our y's, and then we've got our z's on the end. Right, so we're just going to use the quotient rule for exponents on each of those. Right, so we've got x to the fourth over x squared. Remember, if we are dividing terms that have a common base, we can subtract their exponents. So that's going to become x to the 4 minus 2. 4 minus 2 is 2. So that's going to be x squared. You can also think of it as like here you have 4 x's, here you have 2. So 2 of the x's cancel with 2 of the x's if you want to think of it that way. All right, we're going to do something similar here with the y's. We've got y to the negative fourth, y to the negative third. They have a common base, so we are going to, and we're dividing, so we're going to subtract their exponents. So that's going to be y to the negative 4 minus negative 3. Right, so be careful there. So negative 4 minus negative 3. So negative 4 minus negative 3, that becomes a plus, right? So that's really, oh gosh, sorry, this is a new pen. And I don't know why it keeps doing that. Right, so this is really like negative 4 plus 3. What's negative 4 plus 3? Negative 1. Right, so y to the negative 1. Right, now let's deal with the z's. With the z's on the end. Z to the negative 3 divided by z to the fourth. We have a common base. We're dividing, so we're going to subtract the exponents. So that's going to be z to the negative 3 minus 4. Z to the negative 3 minus 4. And notice that everything defaults with this quotient rule. Everything defaults up into the numerator, and then we'll have to deal with the negative exponents, so things may end up in the denominator. Right, so negative 3 minus 4. Let's get back on track. Negative 3 minus 4. We need to combine those. Negative 3 minus 4 is negative 7. All right, so that becomes z to the negative 7. All right, now we need to deal with our negative exponents. All right, so our answer is only supposed to contain positive exponents. So we need to move this y term and this z term to the other side of the fraction bar. Right, so the 2x squared is going to stay in the top. Those do not have negative exponents. They don't need to go anywhere. Right, so the 2x squared stays in the top. Now in the bottom, we already had a 3, so the 3's got to go over. And then we're also going to be moving this y to the negative 1 to the bottom. When it goes to the bottom, it's going to be y to the positive 1. And when the z to the negative 7 goes to the bottom, it's going to be z to the positive 7. All right, it looks like I left the 3 off, so let's add that back on. All right, and then remember this was really like y to the positive 1. We don't need to write the first power, so you can see I've left it off there. And when that z to the negative 7 moved to the denominator, that became a positive 7. Right, and there's no other like terms. There's nothing else we can cancel out or combine. So we are all done. All right, and our last one, 4 over 5 in the parentheses raised to the negative 2. We're going to use that negative exponent rule for fractions that says that we can flip the fraction on the inside, and we're going to change the exponent to a positive 2. Right now we can just distribute the exponent to the numerator and to the denominator. Right, so we're just distributing this exponent to the top and to the bottom. So it becomes 5 squared over 4 squared. Right, so 5 squared over 4 squared, which is 25 over 16. Right, so if you want to do an intermediate step, 5 squared over 4 squared, which is 25 over 16. All right, so I know this was a long one. I appreciate you sticking around to the end. If you have any questions, please let me know, and I'll see you guys next time.